Hi everyone. I'm Derek Schultz. I'm your teacher for Plant Science 2. But anyways, um, Plant Science 2. It's a fun course. It's primarily soil science and soil nutrition. So that's what this is going to be all about. It's a foundational course. I hope you find it interesting. Usually students do. I would encourage you to keep on top of the course. I'll do my best with announcements, but I'm not going to hold your hands. You need to manage your time and keep on top of assignments and quizzes. Um, the teaching and learning plan is a dynamic document, especially since this is going online. I have to sort of tweak things a little bit as I go, but for the most part, what you see posted is what you get. Although, don't print it off, put it in the front of your binder, and assume that that's what it's going to be. Go back to the original document. But if you check your emails, you'll see announcements. I'll keep you moving along just fine. But you should definitely use email. Um, Anyways, I guess a little bit about myself. Sometimes students want to know who this person is that's teaching them, and are they just some crackpot who they pulled off the street? Um, and the fact is, I am some crackpot that they just pulled off the street, but no one else wanted to teach, so here I am. No, I don't know. I went to school for far too long. Did a bunch of stuff, bought a farm, ran that for 14 years. I'm in the greenhouse business. That's me. Uh, Primarily did bedding plants for Loblaws for those years. Also did a hydroponic lettuce business for a couple of years, and then someone came and bought my farm, and kids didn't want it anyway. So long story short, here I am teaching. So it's actually quite fun. Enjoy it. Um, what you will find about me is so I'm actually trained as a it won't really make any sense right now, but I'm trained as a molecular biologist. That's what I spent about 9 years doing cancer research at Queen's University, and so I'm a science guy. Okay, so that means that I stick to the facts, and when we get into some topics, I might get crusty at times, and that's because I like to deal with the realm of reality and not what people want to hear, but what we know and what we don't know. And that may seem really obvious to you when I say that right now, but I think as we go through the course, you'll see there's a couple times where maybe you're like, "Oh, I disagree with him," and no, he's so old-fashioned. Maybe I am, but I'm a firm believer in the scientific method, and that means that if someone's going to make a claim, they can, but it needs to be backed up with facts, and then ultimately needs to be reproduced by someone else in a similar controlled fashion, and then we can begin to start thinking that maybe there's some truth to what they said. Um, I know a lot of people like watching YouTube and learning how to grow plants from YouTube, and the internet's a fantastic thing. It's also a horrible thing. Um, because an amateur can reach millions of people with bad information. But once millions of people have heard that, there's this sort of herd mentality that it must be true. And this is sort of the double-edged sword of the internet. So my job as an educator is to educate. That means to bring you up to the current state of knowledge that is both proven and used in industry. And when I say industry, I mean like people who actually derive a living from this, not someone on YouTube who's got a Rubbermaid with some plants in it. It's not their living. It's a hobby. They don't have to pay bills. They don't understand what it means to have to make a profit and keep a bank happy. So I'm going to teach you soil science. Any course you have with me, I am going to teach you as it is done in the world of companies making money and trying to stay afloat. That means positive cash flow, right? So I may come across as a hardline capitalist. I am not. I am not actually not a hardline capitalist. But at the end of the day, we live in a world where you live and die by finances. It sucks, but You all know this. When you graduate, you'll be looking for work, and then reality will start to set in. So I want you to enjoy this course. I'm going to teach you a lot, and I hope you come away with something, maybe a broader perspective than when you started. And if you come back and listen to this at the end of the term, it might actually make more sense. But there you have, I've said it. So let's get going. This is a long lesson, by the way. It's just how the course is laid out. I inherited this and I'm tweaking it all the time, but this first lesson is quite long. But it's a video, so you can stop, go take a walk, get a coffee. So maybe it's perfect. Better here than sitting in a lecture hall listening to Derek. Anyways, let's move on. Okay, enough of that. So, soil, also known as dirt. I don't care what term you use. Some people do, but not me. Soil usage. This is a pretty cool picture showing this is actually a mango tree in a riverbank. Obviously erosion is happening, but what I'm trying to show you here is this is kind of what this lesson is all about, looking at the different layers of soil and what the plants are using it for. In this case, roots are growing into the soil, so they're providing both nutrition and support, anchors. And obviously how we manage the soil is critical to the health of our plant. A lot of times people forget about the roots. They look at the leaves and they're problem solving the top of the plant, but they forget the bottom, which is a huge part of it. So let's look at soil types. This is probably one of the first really interesting surprises you'll experience today. And this is talking about the origins of soil. And the reality is that the vast majority of soil is actually just rock or rock dust. It's inorganic in nature. That means that there's no carbon in it. It's just rock minerals. Whereas organic soil, which is composed of decaying plant and animal in various states of decomposition, that's what we call organic soil. So in this picture of a mountain valley, this actually really nicely shows how soil kind of forms. You've got these mountains, this is the rock, ultimately the bedrock, and as it cracks and crumbles and falls down and breaks into smaller and smaller pieces, and then eventually plants are able to grow and they use some of the minerals and then they die, and down in the bottom of the valley where all that matter seems to flush out, you have slightly more organic content. Not to say that there still isn't mineral, but you have more organic down there. So we have inorganic in the mountains and we have organic in the valleys. Really good high organic content soil can be found just north of Toronto off Highway 400. This is the Holland Marsh. This is where a lot of Ontario's locally grown produce is grown. It's used to be a bog that was drained. There's actually drainage canals all around the perimeter that drain the water out of the bog, and so that really high organic bog-like soil was then drained away, exposed, and cultivated, and produces a lot of fantastic vegetables, carrots, onions, garlic, you name it, that's what they grow there. In nature, organic soils are found obviously in wetter areas, marshy areas, areas where there's more biological activity. So looking at terms like inorganic and organic, I know a lot of people when they hear the term organic, they're thinking pesticide free, that kind of thing. But really the term organic existed a long time before that crowd absconded the name. And it actually means it's anything that is derived with carbon in it. So living matter, whether it's plant or animal. We are organic because we take in hydrocarbons like sugars and we incorporate the hydrogen and carbons into our molecules. So we are organic. Whereas inorganic means that these are mineral salts that are derived from actual just elements from the periodic table. Bound together as crystals, There is no hydrocarbon element in those rocks, though. They're just, aluminum or copper or iron or calcium. So I just wanted to clarify that. We will look into some other types of soils in the course later, what we call soilless media. So these are human-made or processed soils that don't actually contain mineral soils. So there's no inherent elements like aluminum, copper, calcium, iron. They are strictly hydrogen and carbon, like peat moss and coconut coir, because they are just plant material. And plants, we know, take in water and carbon dioxide and they stitch them together to make hydrocarbons. So what do mineral soils bring to the mix? Well, lots, but let's look at this a little more. So soil can be defined, here's your first definition to remember, as the unconsolidated material on the surface of the earth that serves as a natural medium for plants and animals. So unconsolidated, I put a link here. For what it's worth, the slideshow, by the way, is posted as both a video and traditional PowerPoint. The video doesn't enable hot links, as far as I know. So the original slideshow will actually, all these links will work. If you go back, it would be important for you to do that, to click on some of the links that bring you to definitions and websites and videos. I just want to point that out now while I think of it. But unconsolidated means at one point the soil or the mineral particles were all one piece, or what we call consolidated. But as they become soil, they break apart into small pieces, so they're unconsolidated. Organic soils are those formed from dead plants and animals. I know I'm repeating myself, but repetition seems to help clarify things and keep facts straight. So mineral or inorganic soils are derived from rocks. So organics derive from dead plants and animals, and mineral or inorganic soils are derived from rocks. 95% of soils are actually mineral. 95%. So even in your average garden, you take a handful of soil, put it under a microscope and look at it, you are going to see lots of quartz crystals and granite crystals and whatnot that will make up quite a significant portion of what you have in your hand. So mineral soils are not to be ignored. They are primarily where we get a lot of our nutrients from. When you think about it, organic, strictly hydrogen and carbon in the root zone is not very useful to a plant. They take in their hydrogen as water and their carbon as CO2, not from the roots. So organic soils don't have much to offer in the way of minerals that inorganic rock soils do. So obviously, if you're growing in purely organic soils like peat moss or coconut coir, you need to supplement with everything under the sun to make sure the plant actually is happy. So looking at a riverbank, we can get a sense of what a typical soil might look like. And here we have an eroded slope where the bank has collapsed. And only the very top layer is where grass is growing and dying, where we see there's some organic. But everything down below is sandy, mineral-based soil in this context. Looking at a typical forest, what does nature have to show us, right? So this is spring right now, which is an interesting time to see differences in the soil in the forest floor. And what we're looking at here is in a low-lying area, we have a lot of green stuff, and on the slopes, we don't. And what's going on here is that in the low-lying areas, we have moisture, wet, moist soil, and that supports a lot of organic growth, which grows and dies and grows and dies, and over years builds up that organic content. Where on the slope, where it's well drained, we have less plant life growing and slower accumulation of organic soils. So going back to what I said earlier about the Holland Marsh, down low with lots of water, lots of plant life, high accumulation of organic content, which is, good for certain things, obviously. Now, I did mention that mineral soils are where we get our nutrients from. So if you're paying attention, you may say, well, Derek, why is it that the plants are growing where there's more organic stuff? Well, as you go through the course, you'll learn about properties of soil related to oxygen, um, moisture retention, in addition to nutrition, right? Nutrition alone is not all we need. So that sort of nice, porous, spongy organic soil gives the roots that happy zone they need. But there's also the minerals down below, which the roots can access to get nutrients. Plus, whatever runs off here into the organic will feed it with minerals that the plants need. So all is not lost just because there's more organic down there. So organic soils are usually in low-lying, poorly drained, which means wet, areas. Usually it's dark in color or high in what we call humus. So bog-type plants, skunk cabbage, whatnot, they grow in these areas in the wild. Um, let's look at humus. I don't mean hummus, I mean humus. What is um, so as plants grow in soil and die, they incorporate minerals from the ground and carbon dioxide and water, and they grow cell walls. Cell walls are really fascinating structures. I've got a picture here of a rebar enforced concrete wall. So here, these black lines are steel bars. And when they build buildings, they put steel in and then they surround it with concrete. That's what we call rebar. And when you look at how a cell wall is formed down here, you can see we have cellulose. This is like the rebar, right? Just like the picture above. And then it's surrounded by all these molecules. And plants are pretty cool in how they lay down their cell walls. When you look at a plant that's just growing a brand new leaf, the leaf is usually very delicate, soft, maybe even hanging a little bit. Again, springtime is the perfect time to see this happen in real life. So over the next couple of weeks, I really encourage you to go out and look at trees as their leaves open. Now, inside a bud all winter, the tree has actually been forming their new leaf. It's pretty much essentially fully formed. And so as spring arrives, water starts to infiltrate into the roots, up into the tree, and the tree pumps the water into the buds and basically inflates the leaves. And they'll get bigger and bigger, and the cells get further and bigger in size, and the leaf expands until it's fully grown. And if you can imagine these cellulose fibers being around all the cells in the leaves, those fibers can stretch and adjust as the cell expands. So that's why young leaves are very soft and pliable. Once the leaf is fully grown, the plant actually pumps out several molecules that react almost like an epoxy. So it makes them inside the cell, pumps them outside, and then they harden around the cellulose, just like concrete. Once that has happened, the leaf will no longer change shape significantly. It's hardened. Why am I going through this long story? Because when that leaf ultimately dies, falls to the forest floor and begins to degrade, the cellulose, which is sugar-based, is rapidly broken down by bacteria and fungi, and leaving behind these lignin-like molecules, which are a lot more difficult to break down. And it's these exterior molecules that are what we call humus. Even humus eventually breaks down. Fungi, some specialized fungi are very good at it, but it's very, very resistant to degradation. So it does last for quite a long time. Essentially, if you look at a log laying in the forest floor, it will take many years to break down. And the cellulose in the center is often the first thing that's gone, which is why when you look at a dead log and pick it up, it's actually fairly light and spongy. That's because the cellulose has been degraded by bacteria, and you're left with the exterior core of lignin, which is a bit more like a rubbery kind of structure. So that's humus, and that's where it comes from. Not hummus. Okay, soil phases, fancy word here. What are we talking about? 3 phases. solids, liquids, and gas. Just like water, right? You got your ice cube and vapor and liquid. But in soils, the solids are both organic and inorganic, which I've introduced you to. Liquid would be water and dissolved nutrients, and then gases that are in the soil amongst the different particles. Those gases are critical for root respiration, right? That's the ability to breathe. You should have learned that in Plant Science 1. Very critical to understand that plants consume oxygen. I know a lot of the times you talk about plants producing oxygen. Yes, they do, but they consume oxygen all the time. Anywhere where there's physiological activity, we have respiration happening. It's just that in certain times of the day, the plants produce excessive oxygen relative to what they consume. But if you think about it, roots are not exposed to the sun. They're not producing oxygen, but they're alive, so they have to consume oxygen. So we need to make sure there's enough gas in the soil, which means prevent flooding, right? So here's my little Venn diagram. Solids made up of organic and inorganic materials, liquids, water, dissolved nutrients, and gaseous phase, which is air and other gases that are between the soil particles. Percentage-wise, we're looking at 50% solid, 25% liquid, and 25% gas, typically. You have a lab coming up, I think it's your next class, where we look at measuring the different volumes of those both liquid and gas in a soil sample. You can use that to determine if the soil sample is suitable for your plants to grow in or not. So, what percentage of soils are organic? Review question. What percentage? 5%. Not a lot. A vast majority of your soil is actually mineral. Soils derived from rock are called mineral, inorganic, organic. A and B, A and C. Well, the answer is mineral and inorganic. This question is just to remind you that these two terms are essentially related. Normally the percent solid in the soil is, wait for it, 50%. All right, let's look at soil formation, right? Formed from weathered or consolidated or unconsolidated parent material, right? That's where it comes from, so rocks. Parent material is the type of rock which a certain type of soil is formed from. And parent material influences soil characteristics. So what we're talking about here is the type of rock, right? So if I've convinced you that 95% of soil is actually mineral, then we need to know what kind of mineral that is. For example, limestone, which is sandy and basic, or granite, which is acidic. All right. This is an acronym that you'll need to remember for your midterm and quizzes, CLORPT. I've posted a video on week 1 folder, which you should definitely watch. It's also linked in the PowerPoint slides that are matching this. CLORPT is an acronym that helps us remember all the things that go into soil formation. So we're going to go through these things like climate, organic or organisms or organic matter, relief, which is like the topographical nature of the land. Is it mountainous? Is it rivers? Parent material, we just alluded to that, the type of rock, and then time. Obviously, forming soil, we're talking really long periods of time. And many times people add H to the end of this because we are finding that humans impact soil formation significantly with urban development and modern agricultural practices. So we are not insignificant in this formation pathway. There's the link in the PowerPoint slides. Click on that, watch the video. You have to scroll down just a little bit to see the video, and then I think it's University of Manchester. That's a really good video that helps explain the formation of soils. Okay, so let's start looking at the CL part of CLORPT, which would be climate. So if it's a warm, moist area, soils typically develop quickly, whereas in cold, dry areas where there's not a lot of precipitation, that's your worst case scenario. It takes a very long time for soil to form in that context. So climate plays a role. Climate plays a role in terms of weathering. So action by which rocks are gradually changed to loose material. How does that work? Physical weathering, right? So mechanical breakdown. So wind blasting rocks or grit against other rocks, sandblasting them over many, many millennia, or rain causing rocks and smaller rocks to cascade down slopes, knocking each other and breaking into finer pieces. And one we see often in our area, which is freezing and thawing. So as water moves into cracks and freezes, it expands, and that causes rocks to crack and split open. Then there's chemical weathering, right? Breaking down due to chemical reactions. Anytime water passes through our atmosphere, so rain, it's exposed to all the gases in our atmosphere. And carbon dioxide is, as we all know from the news and whatnot, is something that's in our atmosphere and in growing concentrations. But regardless, carbon dioxide interacts with water to form carbonic acid. So all rain is slightly acidic. And this has nothing to do with your diesel truck or industry. It is slightly acidic because of just the simple action of water interacting with carbon dioxide. Now, what is interesting about that is that as carbon dioxide levels increase in the atmosphere, we do see an overall increase in acidity. And what do those acids do? Well, they break down rocks, they break down minerals, they accelerate the degradation of materials. This is a picture showing frost wedging, right? So you've got a small crack in your rock, water seeps in, and in the winter when it freezes, it cracks it open. You may be wondering why that happens. Water molecules, when they are liquid, they can fit really close together to each other, right? Tightly packed in your glass of water. As soon as you turn it into ice, they are forced to form crystals. Think of it like this. And those crystals are less dense because they can't pack in close like this in a water droplet. They're spaced out, which is why your ice cubes float in your drink. But the simple act of going from a liquid water to frozen means it has to expand, and the force that's between the water molecules to make this crystalline structure is so strong that it cracks the rock open. And this is probably the #1 starting point for where we go from consolidated rocks into smaller rocks, which then will continue to break. So if you look at a mountaintop, as frost wedging cracks the rocks at the top of the mountain open, the smaller pieces that crack off fall down the slope, tumbling and breaking into smaller pieces, and then the rain washes them down and smaller bits knocks pieces off and eventually end up with very small particles. This is over here is the Niagara Escarpment. This is really classic frost wedging. This is someone found a nice piece of limestone laying in the ground, and the rainwater and subsequent freezing has literally cracked that piece up into all sorts of puzzle matched pieces. So frost wedging is the first step really in rock and soil formation. So chemical hydrolysis, water reacting with parent material, acidification, right? The idea that acids form and etch the parent material, knocking little bits of atoms off, solubilizing, basically dissolving the rock. Oxygen is another one. Maybe a lot of you have a used car. Being students, you probably understand what rust is. That's the act of oxygen reacting with atoms and changing their structure, or their chemical state, so that they basically fall off whatever parent material they're on. In our case, your fender falling off. In the case of a rock, it would be metals and elements that are oxidizable eventually coming off the rock through oxidation. This is a picture of some rocks that are showing some of it is rainwater slowly working its way down a slope, dissolving the rocks. Some of this might have been glacial scraping, but a lot of this, looking at the structure, it's actually, this would be rainwater etching over thousands of years. And all the material that's been etched out has made its way down towards the body of water that's down there. So hydrolysis, acidification, oxygen. Looking at a dry climate, this is basically, we're looking at maybe a little bits of rain here and there. This is very, very old, sort of dune-like structures that will probably be millions, if not billions of years sitting there, very, very, very slowly forming soils. So, talking about water in the weathering process, it's important that you learn about two terms, eluviation and illuviation. Again, these links will work in the PowerPoint, but not in the video. So make sure you go back and follow these links. But I'm going to help you understand what they are. So eluviation means that at the surface of the soil, whatever's happening, let's say it's weather is breaking down material, making smaller and smaller particles and minerals that the plants ultimately will want to use, but that's not their goal. They're making these little particles. As you get rain, those particles will drain into the soil and be carried down. We call that leaching. So it will be leached down further into the soil. So that's the zone of eluviation. To help you remember this, eluviation starts with an E, so think of the word exit. So the eluviation zone is near the top of the soil, where minerals are exiting and being leached deeper down into the soil. The illuviation zone is where those leached particles are arriving. So they can't fit any further. It's like going into a filter. Eventually the pores get so small that those particles are trapped. That's the illuviation zone. That's where the leaching particles arrive. This is a picture that will help explain this. So here we have the particles leaching down into the soil from the illuviation zone and arriving at the illuviation zone, where they no longer can penetrate deeper into the soil. What's interesting about this is that depending on the climate, so here we have a wet, humid climate, here we have a semi-arid climate, let's say like Ontario, and here we have a desert-like climate. Notice the illuviation zone is at different depths. So where there's lots of rain, illuviation zone's deeper because the rain percolates that much further into the soil, getting that layer down deep. In the semi-arid zone, it is less deep because there's less rainfall. And then in a desert where there's little to no rainfall, the illuviation zone's at the surface. Now, this is relevant because all those minerals that have been broken free from the soil, which are now accessible to the plants because they can absorb them into their roots, that's the zone where there's a lot of nutritional value for the plants. So here, roots need to go deep to find those areas. Same here, it's about intermediate. And then, of course, in the desert, it's on the surface. It's very shallow. You can see if you're, for example, a tree, you can have a nice deep root structure here that will anchor the tree well as it moves down looking for that illuviation zone where all the nutrients are. In the prairies, where our illuviation zone is maybe a little less deep, you'll see that there's fewer trees. It's more of a grassland. And then in the desert, you won't find trees. And if you did, their root zone would be so shallow that the slightest wind, the tree would fall over. Because there's no incentive to go down here for nutrients. It's all in this illuviation zone. I've really made a mess of this slide. All right. So there we have the illuviation zone and illuviation zone. So make sure you understand the differences between those two terms. Wind is something I alluded to. If you've ever been to the Alberta Badlands, you'll see how wind impacts the erosion of soil, blasting the rocks with sand, helping to break them down into smaller particles. So, a factor. Let's move on to O, organisms. So, plant roots themselves are actually very powerful at splitting rocks. Maybe you've seen roots lifting a sidewalk in an urban setting, but roots will penetrate down into cracks and eventually through water pressure split the rocks open, which will accelerate the soil formation process. Both earthworms and rodents dig holes, and rain percolates deeper into the soil through those holes, which also accelerates the formation of soils. And then on this last rock over here, I have a photograph of something called lichen, which is actually a bacteria and fungal symbiotic relationship. But they produce acids, and a lot of rocks in Ontario, for example, the Canadian Shield, one of the ways they are mineralized is through the acid that is released from these lichen, and eventually just eats away at the rocks, releasing nutrients. Every time it rains, some of those nutrients are lost from the lichen and percolate down into the surrounding soils, which then the plants can use. Ultimately, the rock would become weakened and accelerate the soil formation process as well. Okay, so as organisms die, they leave organic matter behind. We know that, that's fair. Organic matter accumulates, obviously near the surface is where we have most of the biological activity. So that's where we get a lot of the organic content from organisms. It is important to know this point here, organic matter is dynamic, meaning that it forms fairly quickly, it also disappears fairly quickly, right? So organic matter like this will continue to degrade, which means it's forming carbon dioxide, CO2, I'm going to try to write that, you know what that is, which is a gas which evaporates into the atmosphere. So this is a dynamic layer that is cycling all the time. So it is looking at this from a geological time scale, you know, hundreds of thousands of years, if not millions. Organic content really is maybe more on the hundreds of years scale. And so it comes and goes depending on how successful the plant material is on the surface. Let's look at topography, so relief. The geologists like that term. So depending on the shape of the land, that dictates how wind and water flows, which then impacts the material breaking down. If it's a steep slope, there's more erosion, like in the Grand Canyon here. As that erodes and the rocks hit each other and knock and break into smaller pieces, and then the fine particles are carried away in the river, where those fine particles will be deposited as silt, which is a nutritious mineral soil. In this rocky mountain scene here, we can see that the snow, which ultimately forms glaciers, which grind and crush and scrape minerals off, rains out of the bottom will contain those fine particles, which ultimately turns into your mineral soils. Sorry, I skipped that slide early by accident. For some reason, this doesn't have a back button, but that's fine. I alluded to this earlier in terms of looking at the parent material, the type of rock. I wanted to repeat this because it's worth noting. Looking at the parent rock in a given geographical location will give you an indication of the soil's properties. So in Niagara, we have a limestone Niagara escarpment, whereas if you're in Muskoka, where it's predominantly granite, right away you can recognize that the granite soil is going to be an acidic soil, and the limestone is going to be a basic soil. So understanding what type of parent materials in your particular area will give an indication of what type of plants are happiest growing in that context. Lastly is time. I alluded to this already a couple times that we're talking about very large time scales here. on a geological scale, this can be meaning hundreds, if not millions of years. But let's just say for less than a millimeter of inorganic soil to form, we're looking at many hundreds of years. So for a fraction of a millimeter, it's several hundreds years to develop. Where organic soils develop fairly quickly, on average 500 years to generate about 20 millimeters or 2 centimeters of depth. Whether it's mineral or organic soil layers, what I want you to appreciate from this is how valuable soil is. If we're talking about you picking up a handful of dirt and recognizing you're holding something that is ancient in your hands, that's kind of a humbling thought, especially when you see soil that's treated poorly, allowed to erode and wash away. It's a real valuable resource, and a lot of farmers recognize this, which is why they try to adopt practices that minimize runoff from their fields. In the winter, they might put snow fences along the sides of highways to try to break the wind from blowing away the fine layers of their soil. You might say, well, what will they save? I don't know, but you'd be surprised if you have a bare field, say there's not a lot of snow that year, or the wind blows the snow off your field. As the soil dries in the winter and the wind pushes on it, it will knock grains of soil off the field. And over the span of 20, 30 years, you can lose quite a bit of soil off your field. And that's a valuable commodity. Organic soils, obviously, they form more quickly. But I do want to emphasize this, and I'll come back to this. But, whoops, that's supposed to be an eraser. But the mineral soils or inorganic soils are where you get your minerals from, okay? And your organic soils actually are nutrient poor. Again, this is a concept a lot of people really struggle with. They think, well, wait a minute, it's an organic soil. They tend to be nutrient poor. Thinking about it like this, if our rocks are where our minerals originally come from, right? So when I say minerals, what are things that plants need? Well, plants need zinc, they need copper, iron, calcium, manganese. The list is long of all these minerals. Those are derived from the Earth's mantle or rocks. You can't make those atoms. Those atoms were formed in a star, and then it exploded and went into space, and it accumulated into a ball we call Earth. You can't make them unless you have your own personal nuclear reactor. They're just recycled on Earth nonstop as we go about our business. Organic stuff, which is ultimately just hydrogen and carbon, the only minerals that are present there are the minerals that were in the plant material that originally got it from mineral soil and were grown in the organic soil. So you can recycle what nutrients were in the plants and animals in that soil, but all things being equal, you would be very, very hard pressed to achieve even 50% nutrient recycling in just organic soil. So you would become nutrient poor very quickly. That will become more evident as I talk about tropical soils in a bit, but just keep that in mind. So mineral soils is where your nutrients are ultimately coming from. So there's CLORPT: climate, organic matter or organisms, relief, parent material, and time. I'm going to suggest you hit pause, go have a break, come back. I know I am going to. Okay, so let's look at our next part of this lesson, which is talking about soil profiles. So a profile is a cross-section through soil that reveals all the layers underneath. A lot of soil scientists have a special little auger that you kind of twist and it cores deep down into the soil, and you pull out the core, lay it on the ground, and you can see all the different layers that make up the soil underneath your below the surface. So, I mean, the next time you dig a hole, and I'm sure some of you have dug a hole, you'll notice that the color changes as you progress deeper down through the soil. And that's you moving through the different layers of soil. Basically, you're looking at an evolutionary snapshot of the soil as it's formed in that context. Here's some pictures showing lots of different profiles. So for example, here we've got a very thin organic, dark organic layer at the surface, and then basically it looks like a few very thin but finely packed layers. This is a very gray limestone-ish soil. Here's a thick organic layer. Look at this nice deep organic zone. You can even see some parent material. This is probably near a riverbed. That's still somewhat consolidated. And this is an interesting soil. We're going to look at the very end of the lesson today. We're going to look at PEI as a case example, an extreme example of soil formation. If you look carefully at this soil, it is pretty much ubiquitously one thing, and it's red soil. It's derived from sand. So wait till we get to that those slides, and we'll talk a little bit about PEI. So before I get into all the little terms, let's look at the more common terms that are used for what we call the basic layers of soil. So topsoil, we've all heard of that before. Subsoil, if we haven't, it makes sense because it's below, sub. And then bedrock. So these three terms are very generic, and for a lot of horticultural purposes would suit you just fine. But essentially we're looking at the humus in the topsoil. That's basically your organic layer. Subsoil, where there's less, maybe some eluviation has taken some of the organic matter deeper and it's sort of washed into a smaller content. And then bedrock obviously is ancient stuff that's outside the use of your plants. Now, looking at some more specific terms, we have O, A, E, B, C, and R layers. Each one is called a horizon. So it's important that a profile is made up of many horizons. So looking at the O horizon, this is where we get our humus or our organic matter. A, our topsoil, is where we have vast majority is mineral based with some organic that has illuviated into it. Then we have an even deeper illuviation zone, and down here in the subsoil is where everything has illuviated too, right? This is where we get into the really fine, maybe clay-like particles that have washed their way, trickled deep down into the soil, forming a dense layer. And then there's our parent material. So as far as knowing these layers, it would be helpful if you remember that O is organic, A is topsoil, E is the illuviation, B is the subsoil. It would make so much more sense if it was A, B, C, D, E, but this is how it's done in the industry, so there you go. This is a zoomed in picture to help you kind of get a sense, right? So the organic or O horizon, surface litter, partially decomposed organic matter. The topsoil or A horizon, which is still humus, but you have living creatures, and the vast majority is inorganic minerals. Then there's the illuviation zone, where smaller particles that are breaking down are released and leached deeper into the subsoil. Yet another picture giving you another snapshot at this. I have extras in here because some students struggle with this part, so there's lots of different slides for you to look at to help you study this. Okay, so I've got a picture of a tropical soil profile, and I will come back to tropical soils a few times throughout the course, and one of those reasons is because tropical soils are much, much older than soils in our temperate climate here and closer to the north. When you think about it, it's warmer, there's more precipitation, And because it's warmer, there's been biological life and activity for many, many millions of years more around the equator than there has further north. So the soil is a lot more weathered. And that sort of helps make clear the differences between weathered and unweathered soil. So keep that in mind. So tropical soils are very weathered. So soil formation, it's generally formed in layers, right? That indicates the history of soil layers. Each layer is called a horizon. As far as soil classification goes, we've got things like profiles, horizons, topsoil, subsoil, uh, and bedrock. Just reviewing some of the terms that you should know for the midterm. Here's a couple of examples of soil profiles from, on the left is a deciduous forest. So these are hardwoods. And on the right is mainly conifers. So pine, spruce, whatnot. You see a difference right away. The dark organic layer that we're used to is present in the deciduous, but is mostly absent in the coniferous forest. This stems from the fact that deciduous forests tend to support understory life. So there's young trees and plants growing, and their growing and dying cycling produces organic matter. Whereas in the coniferous forest, those types of trees tend to suppress growth underneath them. I'm not going to test you on this, but it's a term called allelopathy, where basically the needles and whatnot that fall from the tree impact the chemistry of the soil and discourage the growth of other plants. And so that discourages the development of a strong organic layer. So again, in the deciduous forest, we have a dark O horizon, and in the coniferous, we're missing, or it's very negligible. So here's a picture. On the left is our deciduous forest, and you can see there's lots of understory growing under the trees. So and they're also dropping their leaves, which is leaf litter in the fall. That all turns out to mean that there's more organic content and recycling happening in that forest. Whereas in a coniferous soil, there's not a lot of leaves falling. They're slow, but it's not a deciduous forest that drops everything in the fall and then regrows everything the next year. It's incremental. And because there's this term down here, I have a link to it, allelopathy, there's suppressed growth under here. There's hardly any understory. So there's a lot less organic matter in that context. While we're on this slide, looking at the deciduous forest, a lot of times people will say, well, the deciduous forest is so productive. Look at all the plants that are growing. They don't need fertilizer. That is absolutely true because there is what we call nutrient recycling happening here. I know people have heard about things like permaculture on YouTube and stuff like that. It's sort of an attempt to recreate what happens in a natural forest for food production. But there is a real flaw in that logic, right? If you were to grow produce in a forest, right, and then you take that produce home, which means you leave, and you eat it at your house, and you go to the bathroom and it flushes away somewhere else, you have removed nutrients. You're not recycling anymore. It's been removed. So you're breaking the cycle. And that's the major flaw with permaculture ideas, in the sense that unless you're 100% nutrient recycling, it's a myth. And I spent a lot of time debunking some of the ideas around that stuff, but whatever. Going back to my talking about tropical climates and soils, in this concept of nutrient recycling, a lot of times people think, well, in a tropical country, they're so productive, there's plants growing everywhere. And that is 100% true. You walk through a Brazilian jungle and it looks immensely productive, but you have 100% nutrient recycling happening. Perhaps you've heard of this idea of farmers in tropical countries will burn down or plow over the jungle and plant bananas. All right. Now, what you've done essentially is you've disrupted the nutrient recycling. First of all, you've removed the trees. Then you've grown a crop where you take the bananas and you ship them to North America so people can have bananas with their lunch or breakfast. And those nutrients are no longer recycling. They're gone. They're being extracted and sent away as produce. And what ends up happening is the soil becomes very unproductive very quickly, owing to the fact that tropical soils are highly weathered, so they don't store a lot of nutrients. They have a warm, moist climate, which encourages rapid nutrient recycling, which gives the illusion that there's lots of nutrients there, but it's just that it's being rapidly recycled. And then when you take the trees and stuff away that are dropping nutrients into the ground and pulling nutrients up from the soil and contributing to this recycling, if you break that cycle, you lose all the nutritional value that was in the soil at that time. So that's kind of a cautionary note. Help you understand how soil and nutrient cycling is really important. This is a little picture showing a tree struggling in poor soil. So you look at the soil, you don't really know what's going on below the surface. But the fact that there's lots of suckers coming from the base of the tree is telling us that the tree is unhappy. It's looking for something new. It's unhappy. It can't support growth on the main leads. So that's the first indication that something's wrong below the surface. So if you do some core samples and look at the soil, here you'll see that, first of all, we're looking at mostly gravel, and there's a organic layer at the top followed by gravel below. And these are trees that were planted in very poor soil. Maybe some organic matter was added at the top, but trees need their roots to penetrate deeper into the soil for anchoring. And if they don't get that, they're going to be unhappy and they're going to produce those suckers as evidence. So it's important to know whether it's just gravel or maybe a layer of organic matter with gravel underneath. This is not an ideal soil to grow in. Extreme example, but you definitely want to consider below the surface. So, some review questions. What soil horizon develops first? A lot of times people think organic, but let's talk about parent material as the very beginning point for soil, okay? What horizon, or the horizon that has a lot of organic matter is, well, that's pretty easy, right? It's organic horizon. So lots of humus. Collectively, the horizons are called, which one of these? Parent material, cross-section, or profile? Profile. Organic soils, all right, they form quickly, take thousands of years to form, are mainly composed of dead plants and animals. Which is it? B and C, or A and C, or A, B, or C? So, organic soils form quickly, we talked about that. Mainly composed of dead plants and animals, correct. Now, we talked about organic soil forming on the scale of hundreds of years, not thousands. So it's fairly quick. So A and C would have been the correct answer. All right, I want to look at a little bit of a case study here. This is Prince Edward Island. It's an interesting place, interesting soil. PEI, the topography, is actually a lot like Southern Ontario. It's just sort of rolling green agricultural hills. So not a lot of mountains. It's fairly flat. Weather, it's cool, rain, it's sort of typical, moderate climate. What is the parent material? I mean, here, look at this. There's the ocean. We're looking at these highly eroded banks. PEI is made of, the entire island is sandstone, or more specifically, red sandstone. It erodes quickly. Look at these shorelines, they're falling apart. Sandstone essentially is is oxidized iron, so lots of iron in it, and it's rusty colored because it's oxidized, just like your old fender in your car. Um, Looking how the soil forms, originally PEI would have been granite, right? That formed somewhere on mainland. And as it weathered, it formed ultimately red oxidized sand, which was deposited, whether it was glacial or what, we don't know, pushed out as a giant pile called PEI. And the weight of the sandstone actually recreated, the weight of the sand actually recreated stone below the surface. And these are rocks that are actually compressed sand. So it started as granite, which was consolidated, formed 100% unconsolidated sand through glacial action or whatever was pushed out as a pile, and the weight compressed it into sandstone. And the island now is slowly eroding back to sand as it's exposed by the ocean. So PI is a red sandy soil, a red clay sand type soil. What is good about that? Well, from a PI perspective, it's great for potatoes. Considering the entire island is just a big pile of sand, there's no stones per se. The surface is cracked and broken down into red soil, which is acidic because its parent material was granite. And the acidity actually suppresses potato scab. These are pictures showing what potato scab looks like, which interferes with the quality of your potato. So if you can grow potatoes without scab, you get more money. So obviously PI is known for its potato growing. Potatoes evolved in red, sandy, acidic soils. So PI turned out to be the perfect place for us to grow potatoes in North America. This is Peru. Notice the similarity, red, sandy soil, acidic. Peru is where potatoes originated from, right? Not PI. We brought them up. There's, I think, thousands of varieties of potatoes that are grown in Peru. Here they've terraced it to minimize erosion because they recognize the value of their red soil. But yeah, potatoes were from Peru. And talking about erosion, on the left here, you can see as water drains from the potato fields, and heads its way back to the ocean, it takes with it soil particles. So the farmers are having to contend with this. Some of the classic PEI coastal vistas will show erosion on a colossal scale. It's fairly soft bedrock or sandstone, which at the surface forms this red soil. Hurricane Juan, it's estimated, washed away almost 5% of the island's topsoil at that time. So erosion can be a very serious issue for PEI farmers, and they have to put in dams and weirs to try to keep the soil from washing into the ocean. Otherwise, they end up with thin, coarse soil that won't grow anymore. So, all right, PEI soil is good for potatoes because it is basic, acidic, or because it's just red. Acidic, right? That discourages the growth of potato scab. And that brings me to the end of this class. We've covered a lot of material. When you're going to be doing your labs, I'm hoping you can source some of the material at home. I've recorded some videos that will demonstrate what I'm looking at, and hopefully you find it interesting. This online thing is definitely challenging, but I think for the most part, we can do some of these labs at home. So you'll notice in week 1, there's a folder that says labs. That's where you'll find the content that you need and instructions. So be sure to follow through on that. Okay. I put lots of information in each week. The first few links are important. After that, it's just if you're interested and you want to read further.